In previous video lectures, we've been talking about how the speed of light is an ultimate speed limit. And in this video, we want to actually look at a case where it seems like you can go faster than light. And so we're going to see how this works out. This is a sort of a fanciful situation. As you can see, we're going to have a trip from San Francisco to St. Louis in the middle of the United States in the Midwest, and then all the way to New York there. This is also a nice example because things like this actually happen in certain astronomical observations where it seems like things are moving faster than the speed of light, especially when you have these very energetic jets that are shot out of quasars. If you know a little bit about astronomy, which very energetic galactic nuclei where there's a black hole in the center and a lot of interesting things going on. It seems like when you observe them over time that they're actually moving faster than the speed of light, but it seems like if you really analyze it, not only seems like, but it is such that it's not really going the speed of light. Situations like that aren't too difficult to analyze, but they require a little trigonometry, so we're not going to tackle that in here. Instead, we're going to use this example, again, San Francisco to St. Louis to New York, so we'll explain what's going on here. It also allows me to do, at this point, to introduce a book to you that, for those of you who want to take it to the next level after this course, especially using a quantitative approach, it's an excellent textbook to do that with. I will give you a list of other books as well. In fact, I have a copy right here. It's called Spacetime Physics. I'll write this up here, by Edwin Taylor and John Archibald Wheeler. So Spacetime Physics. By Edwin Taylor and John Archibald Wheeler. Really a classic in the field. It's in the second edition. We didn't use it for a textbook in this course. We could have, but the material we're covering is certainly less than half of what's in this book. It's not overly expensive, but you can get it online probably for about $60 US new, or used maybe a little less than that, but obviously it costs some money to do that. But it is a type of textbook, and if you want to go beyond what we're doing in this class, it does things a little differently than we've done. For one thing, they like to just get rid of C completely. We've talked about how you can treat C as one, but we keep it around in our formulas. They like to just take C out of the formulas, and sometimes I find, especially for introductory courses, that causes more confusion. But once you've had this course and worked your way through it perhaps a little bit, then Spacetime Physics by Taylor and Wheeler is a classic text in the genre as you will. So and the reason I bring up is this is an example that they do in their book. I've modified it slightly in a couple things, but it's essentially still the same thing. So what's going on here? Well, imagine we're in our spaceship here, or somebody's in the spaceship, maybe Bob or Alice, and they fly by the Golden Gate Bridge in San Francisco here. And when they do that, in a certain velocity v, they have a flash of light at that point, and we take a snapshot, as it were, if we wanted to. And then they keep flying across the United States, and St. Louis is about in the middle there. St. Louis, you may or may not know, has a famous gateway arch there, and so they fly by, or maybe even fly under the gateway arch there. And when they do that, they have another flash of light, so that's flash number 2 at time t2, whenever they reach there. And then they're flying on to New York City at that point. So what's going on here? What's going to happen is the observer at New York City is going to observe these flashes of light coming by. So the first flash of light contains an image of the spaceship and the Golden Gate Bridge. So it's when the spaceship was at the Golden Gate Bridge, moving by there. And so that's represented by this green flash. So it's traveling along here across the United States towards New York. Meanwhile, of course, the spaceship is also traveling that direction, but not as fast. V is going to be less than C, of course, so it's moving along too. So then when it gets to St. Louis and the Gateway Arch because it was like the gateway, St. Louis in many respects was the gateway to the western United States as Europeans moved across and others as well. So the Gateway Arch there. And in flash number 2 here, they take a picture of the spaceship and the gateway arch. And that also then goes in this red flash of light, just color-coded here. So this red flash of light contains the image of the gateway arch and the ship at the gateway arch. And so then at that point you have these 2 flashes of light containing these 2 images, one originally from San Francisco moving across and one from St. Louis. And of course the one from San Francisco is going to be ahead of the one from St. Louis because obviously the initial flash is moving faster than the spaceship. And so when the spaceship gets to the gateway arch and takes a second flash of light, the first one has already moved beyond that a certain distance. And we'll see exactly how much in a second here. Okay? And then the idea here is these 2 flashes of light are going to approach the observer in New York, who's going to observe them, see them, and is going to measure a time difference between those, the arrival of flash number 1 and flash number 2, with flash number 2 just slightly behind flash number 1 there. So let's analyze this a little bit. The distance from San Francisco to St. Louis is going to be the velocity of the ship times the time difference it takes to get there. Essentially, velocity times distance, or velocity times time gives us a distance. So if this was t1 and this was at t2, so it's just the difference in time, how long it takes to get there and what velocity the ship is traveling at. And we'll just call that, as usual, delta t. So that's the time, and v, velocity of the ship, times delta t, is the distance from San Francisco to St. Louis. And then we're also interested, though, in what is the distance between these 2 flashes that contain, the green one contains the image of the Golden Gate in the spaceship, and the red one contains the image of the Gateway Arch and the spaceship. Well, we know that when the second flash occurs, the green flash has gone this far, and that distance from here to here is just going to be the speed of light times delta t, because the ship went from here to here in delta t, and so the speed of light is going to just go a little bit farther because it's going faster. So it's going from here to here in delta t. So this is snapshot 2, when that flash of light is a little ahead of that one. And so we can say that this distance here between the 2 flashes of light is the total distance from San Francisco to our first flash, which is going to be c delta t, because that's, again, how far it's traveled, minus this distance, which is just v delta t. So the first flash of light has gone c delta t, minus the spaceship distance is covered, leaves us the remaining distance. And that's going to be the distance between the 2 flashes of light there as they keep traveling on toward New York. So c delta t minus v delta t, we rewrite that as c minus v times delta t. So that's the distance between them. And so these flashes keep going on here. Eventually, they get, actually very quickly, they get to the observer in New York. And the observer in New York is going to measure the time difference between the 2 flashes of light. Well, what is that going to be? Well, okay, here comes the first flash of light in. It reaches that. The second flash of light is following along behind it at speed c, and a certain distance behind it. So once the first flash of light gets here, it takes the second flash of light just that amount of distance and time to catch up with it. And that's just going to be the distance here, right, divided by its velocity. Okay, so it's going to be the time difference between the arrival flash number 1 and number 2 is simply going to be the distance between them divided by the speed of light. In other words, how long does it take this rear flash to catch up with the first one? So that means it's going to be c minus v delta t all over the speed of light. Okay, so again, do a little imagination here, thought experiment. So this one comes in, the green one comes in at this point and reaches the observer right here. And at that instant in time, the red one is still about right here, traveling that way, and it's traveling at c still. And so it's just going to take, going at speed c, it's going to take this amount of time, the remaining distance to be covered divided by its speed, and you get the time difference between the arrival of flash number 1 and flash number 2. Now here's where it gets a little interesting, okay? Because you're the observer, say, in New York, and you see the 2 flashes arrive. The first flash arrives and you see the image of the spaceship at the Golden Gate Bridge. And then the second flash arrives, and you see the image of the spaceship at the Gateway Arch in St. Louis. And you say, wow, okay? It went from San Francisco to St. Louis pretty quickly there. In fact, it only took this amount of time to go from San Francisco to St. Louis, because that's the difference in arrival time of those two flashes. And they're just like images coming this way, say. They're images coming to your eye here in New York. And so you see, first one comes in, you say, hey, I see the spaceship at the Golden Gate Bridge. And the next one comes in a little bit later, and I say, oh, I see that same spaceship now at the Gateway Arch. And so, gee, I wonder how fast that spaceship was traveling to get from San Francisco to St. Louis. Well, it's simply the amount of time that I perceived between those two images coming in. I say, hey, here it is in San Francisco. Oh, now here it is in St. Louis, divided by the distance it had to cover between San Francisco and St. Louis. Well, what is that distance? That distance is simply v delta t. So let's put this together now. Again, the observer in New York is going to see a time difference between the two flashes arriving. And those images are just going to contain first the San Francisco image and then the St. Louis image. I say, okay, it went from San Francisco to St. Louis. My perception says that's how fast it occurred. And therefore, its velocity, you have a little room here. So let's see. Let's make a little room in here. Maybe we can squeeze it in the middle. So the velocity here, I don't want to erase this because we're going to use it here. So let's call this the apparent velocity. Okay, this is the velocity of the spaceship according to the observer based on these two images coming in. The first image when it was at Golden Gate Bridge, San Francisco, followed by the second image when it was at the Gateway Arch in St. Louis. And the apparent velocity is going to be simply the distance between here, because you can say, hey, that's how far it seemed to travel. That's v delta t divided by the time difference. Distance divided by time is velocity. And so now we're going to have to erase this a little bit, make a little room. And here's the time difference. C minus v delta t divided by c. Okay, we can cancel the delta t's here. We can bring the c actually up to the top of algebra, and this becomes c times v over c minus v for our answer. That is, and let's check the units. Right, we've got velocities on the bottom. We've got actually a sort of a velocity squared, not sort of, but a velocity squared on the top. Therefore, the units will be a velocity in terms of the cancellation. So it checks out. This is a velocity. So this is the apparent velocity of our spaceship to an observer in New York City there. Well, what is that? Okay, if we use units of c in terms of, as we've been doing, 1 light second per second or 1 light year per year, c just becomes 1. So this then becomes v over 1 minus v. Okay? Well, let's put in one of our typical speeds here. What if the velocity is, say, 0.8 c? Not a typical speed in real life, of course, but for our thought experiments with the special theory of relativity. Let's put 0.8 c in there. Okay? So that means I'm going to get 0.8 c divided by 1 minus 0.8 c, but remember, c is just 1 here in our units. So it just becomes 0.8 divided by 1 minus 0.8. So this equals 0.8 over 1 minus 0.8, again assuming c is 1 light year per year, 1 light second per second. Those are the assumed units. Well, 1 minus 0.8 is 0.2. And what I get here is 4. And remember what the units are. This is a velocity. So if c is in units of 1, it means the units here are light years per year or light seconds per second. So let's just say light years per year. We'll choose those. Think about that a minute. That's 4 times the speed of light. That's 4c. 1 light year per year is c. The apparent velocity, according to the observer in New York, is 4 times the speed of light. And in fact, if you choose another value for v here. If you make it, say, 0.9 c, and put 0.9 c in here, you'll get 9 times the speed of light. Okay? And essentially, depending on how high you make c, you can get very high values that are much greater than the speed of light for the apparent velocity that's going on here. It is really sort of an optical illusion is what's going on. It's because the spaceship, while the flashes of light move that way, the spaceship also is moving at a fairly high velocity in that direction. And at normal, quote-unquote, normal velocities, if it's much, normal everyday velocities, this would be far smaller than the speed of light. But it does show you can get situations where it seems like you can have things that are traveling faster than the speed of light. And what we're going to do in our next video clip, actually, is look at a situation that shows you definitely can't have things traveling faster than the speed of light, or sort of all of causality breaks down. So that's what we're doing next in terms of things that are faster than light, to see that, yes, you really can't have situations like this. You can have seeming situations, perhaps, but in actuality, you can't have things going faster than the speed of light.